Am I audible? Oh. So I welcome you all to the week 3 live interaction session for the course on renewable energy engineering, solar, wind and biomass energy systems. Let's just wait for another 2 or 3 minutes and let us give some time for others to join before we begin our session for today. Okay. Let's begin our session for the day, the week 3 live interaction session. Let me just share my screen. Is my screen visible? Yeah. So, yeah, I'm Pratyumnan, currently pursuing my PhD at Indian Institute of Technology, Guwahati. I am the course team member who will be responsible for conducting the live interaction session every week for the course Renewable Energy Engineering, Solar, Wind and Biomass Energy Systems, offered by Professor Vaibhav Vishant Gaut sir and Professor Anand Lakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati as well. So the week 3 live interaction session we are going to start now, which will be primarily focused towards solving one of the very big problems about calculating the efficiency. If you remember, in the last week we actually went through the different kinds of formulas that is required to calculate the efficiency of the flat plate collector. Our main aim here is to calculate, is to improve the efficiency of the flat plate collector. As I said in the previous class also, the from the engineering point of view, our main aim should be to increase the efficiency of a process at a lower cost. We should decrease the cost of a process. At the same time, we also should focus on improving the efficiency. So we saw a lot of different formulas related to that. So let me just show the last week's screen here. Yeah, it starts here. We saw how to calculate the useful heat gain, that is the amount of QU that is actually taken up by the fluid that is flowing through the fluid tubes, which will be used for other applications. and then we saw through the equations relating to the total amount of the solar flux that is actually absorbed by the flat plate collector. What actually falls on the flat plate collector and what is getting absorbed by the flat plate collector, these two are two different things. The amount of energy that is absorbed by the flat plate collector will be different because of the various kinds of losses that is present in the system and other environmental conditions as such. So we saw how to calculate the relationship between the solar flux absorbed by the flat plate collector and the instantaneous solar flux that falls on the flat plate collector, and then the tau alpha average, that is the product of the transmission and the absorption of the radiations. So, and then we saw about the heat removal factor, the collector efficiency factor and the plate effectiveness factor, and then at the end we moved on towards understanding what is actually the efficiency of the flat plate collector. So, yeah, which is given as QU by SAP. AP is your area of the plate, of the absorber plate that you are using to construct the flat plate collector. So let us today solve a problem, because since we have already seen the way of solving the equations that are involved in solving the problem, let us today actually take up a problem to solve this question and calculate and identify how to calculate the efficiency of the flat plate collector. So, and that is something that is also coinciding with the assignment 3 problems. If you see, there are actually two problems. So by solving this question, you will be easily able to solve those two questions for the assignment. So I have divided, actually the entire question is divided here into three different parts. First part is calculation of all the solar angle of incidence, tilt factor, and then the instantaneous beam and global radiation, and then calculating the instantaneous value of the total solar radiation. Then after that we see how to calculate the angle of refraction. Like as I said, the solar light falls on the flat plate collector and then it undergoes refraction because there is a transparent glass cover, and then beneath that transparent glass cover you have a absorber plate, below which you have the fluid tubes in a conventional flat plate collector system. Of course, there are different types of tubular arrangements within the flat plate collector, but here we have assumed that the fluid tubes are present beneath the absorber plate, which is indeed present beneath the glass covers. So, and then we calculate the solar flux absorbed by the flat plate collector. By using that calculation, we calculate the efficiency. So we have divided this particular problem into three different parts, A, B and C. So let us just try solving them and understanding about how to go with the flow of the process, because it's a tedious calculation. As such, if you see from the week 1, the calculations are extremely very tedious, involving lot of different formulas. So let us actually solve them to have an understanding of how to proceed. Like if suppose you get a problem or you are asked to design a flat plate collector and then you are given with the data, then you should be proficient enough to calculate the amount, calculate the efficiency with which the energy will be harnessed from the solar radiation. So the question 1, the A part, the flat plate collector is installed on a building rooftop in Mumbai. Angle of 30 degrees. So here that angle 30 degrees is nothing but it's basically the slope of the flat plate collector, the angle that the flat plate collector is installed from the horizontal point. So that is 30 degrees and it is actually pointing due south. So calculate the respective angles on 16th August at 14 hours, that is your local apparent time, LAT. So here you are supposed to calculate the solar angle, angle of incidence, the tilt factor. So I hope, since we have actually solved these kind of problems on calculating the angle of incidence and solar angles, we will now find it pretty much easier to go about solving the first question, the solar angles and angle of incidence. So what is angle of incidence? Angle of incidence is nothing but the beam direction, the sunbeam direction and the normal to the surface. So for example, if this is your surface from the horizontal, and then if the, let's say, the solar radiation is falling on this direction, the normal to the surface will be in this particular direction. So this is the surface, the normal will be in this, the sunlight is falling in this direction, so the angle between this and this will be your angle of incidence. So now to calculate the angle of incidence, it's actually a function of many different solar angles, if you see. So we have discussed about a lot of different solar angles, like declination angle, hour angle, surface azimuthal angle, solar azimuthal angle, angle of incidence, zenith angle, yeah, and this and the latitude of the location, and many other different solar angles. So this angle of incidence is nothing but it's a function of phi, that is your latitude of location, delta, that is your declination angle, beta, that is your slope of the flat plate collector from the horizontal ground surface, your gamma is your surface azimuthal angle, that is your the normal to the flat plate, its projection on the horizontal surface, and the south of the flat plate collector. So that angle omega is your hour angle. So for Mumbai, the latitude of the location is 19.07 degree north. This value we have actually taken it from the internet. So this is fixed for a particular location. So if you just use the internet Google, and then if you just Google the latitude of Mumbai, you will approximately get the same value. So now we have to calculate the angle of incidence. So the angle of incidence formula is cos theta is equal to sin phi times sin delta, that is your declination angle, cos of your slope plus cos of your declination angle, cos of the surface azimuthal angle, cos of hour angle times sine of your slope. Similarly, cos of latitude and then the rest of the expression plus cos delta, cos gamma, sine omega and sine beta. So this we have already seen in week 1 as well as in week 2. We have solved almost 3 problems. So now we have to, so now we just know 2 parameters here. One is the latitude of the location, that is 19.07 degree, and then your beta, that is 30 degrees from the horizontal ground surface. Now we have to actually calculate your surface azimuthal angle will be, since this thing is pointing due south, the surface is pointing due south, so the surface azimuthal angle will be 0. So you know 3 parameters. Now there are only 2 parameters left. One is the declination angle and the other one is the hour angle. So you know it's August 16th, so you know the value of n, and then you know the formula for calculating the angle of declination. So I just want from you to calculate and let me know the value of delta, the declination angle. Yes, anybody has found out? Declination angle. So the formula for the declination angle is 23.45 times sine of 360 divided by 365 into 284 plus n, and the value of your n for 16th August is 228. Since we do not know whether the year that we are particularly calculating this angle of incidence is a leap year or not, so we generally assume that the year is a normal year, so it has totally 365 days. The February has only 28 days. So let's calculate the 16th August, what will be the value. Just calculate. So the value will be 31 January, 28 March, April, May, June, July and August. So 228 is the nth value. So here, while calculating the value of n, you have to consider that particular date as well. As I said previously, 16th August has also to be taken into consideration while calculating the value of delta. So this is the delta value. So delta is 23.45 sine of 360 divided by 365. This will remain as constant even if it is a leap year into 284 plus 228. So the value of delta is 13.45. So here we have 228 already plus 284 into 360 divided by 365. Sine of this value is 0.57 into 23.45. $13.45. I guess Vinay Das, can you just mute your mic? Like in case if you don't have any queries. Yeah, thank you, because there was some kind of noise which was interrupting before. So the value as we just now calculated, delta will be 13.45 degrees Celsius. Now you can calculate the hour angle. Hour angle formula is even more easier. So let me just see how many responses I get back from the audience for the calculation of the hour angle, because assignment also has been completed for this particular week. So calculation of hour angle is a week 1's course. So we dealt calculation of hour angle over there. Now I just want to know how many of them actually calculate, because this is very simple. You know the latent apparent time, that is 14 hours, and then you just need to calculate the hour angle. So I just want the values from the audience along with the sign. Anybody? Calculation of hour angle. Okay, so let us calculate the hour angle, and let me just calculate it once again. So the formula for hour angle is the latent apparent time, LAT, minus 12 times $15. So the reason why it is 15 is because the earth rotates for about 360 degrees on its own axis in 24 hours. So the 360 divided by 24 is 15. So here your LAT is 14 hours. So the value is 14 minus 12 into 15. So that is 2 into 15, that is 30 degrees. So what will be the sign convention? Will it be just plus 30 or will it be minus 30? And here you need to read it as 14 hours, it is not 1400 hours. It is usually represented as 2 p.m. it is actually. In LAT it is 14 hours. So since the latent apparent time is after 12 hours, like in the noon, it is after that, it's past noon, so it's in the afternoon, so the value will be negative according to the sign convention. If the value is, suppose let's say it's morning, it's 10 hours, then it will be positive because that value will come before 12 hours, that is the noon. So it will be in the morning. So for morning the sign convention is positive. For the afternoon and evening the sign convention is negative 30. There it is positive 30. So now it's actually, so here we now know the value of phi latitude, delta declination, beta slope, gamma is the surface azimuthal angle and our angle. So we can calculate the value of theta. So the value of theta will be, cos theta is sine times 19.07 into sine of 13.45 into cos of beta, that is cos 30, plus cos of 13.45 is your delta, and cos gamma, that is cos 0, cos omega, that is cos plus 30. So in case of cos there will not be any issue, as I said previously, but in case of sine there will be an issue. So you have to be careful while doing the calculation, because sine of a negative angle is minus sine of that angle, whereas cos of a negative angle is same as cos of that angle, plus cos phi, that is 19.07, cos of delta 13.45, omega 30, beta is also 30, minus sine 13.45, cos 0 is cos of omega gamma, that is your surface azimuthal angle, sine of 30, plus cos 13.45 sine 0 into sine omega sine 30. So sine 0 is 0. So this particular term, that is his cos delta sine omega sine gamma sine beta, the third term will be 0. So if you do the calculation, you will get 0.782. So theta is nothing but cos inverse of 0.782. Since this is a big calculation, I taking this value since it's previously calculated, so I am taking cos theta as 0.782. Let's just now calculate the value of theta alone. So cos inverse, okay, sorry, 0.782, and for that you need to take cos inverse. I guess here we do not have that inverse function. Okay, let me just use my calculator. Cos inverse of this thing value is coming around 38.559. So that I am taking that 38.559 as 38.56. So again I am asking, do let me know if you have any doubts here, because I guess this will be our last session, or we will be having one more session where we will talk about the angle of incidence. After that we will be going towards the other two kinds of renewable energy in this particular course, so like biomass and wind. So we may not be able to come back. So since this is inside the solar radiation, we are able to actually solve this angle of incidence problem again and again, but once we go there then we may not be able to solve. So in case if you have any doubt, please let me know. Anybody has any doubt? Because angle of incidence calculation was not given during the assignment, but again that specific declination angles and hour angle, that calculation was there in the assignment problems as well. So if you guys have any doubt while calculating those, in case of the sign convention, then please let me know now before we proceed towards the other. Is it possible to mute? Yeah, thank you. Yeah, so please let me know now. Or otherwise we can go to the real problem solving for the today, that is calculating the angle of incidence and other stuff. Calculating this instantaneous solar radiation, ITIB, those values we can start calculating.
Sir, can you please move to the first slide?
You mean this one?
This one, sir.
Yeah. Yes. Do you have any doubt in this slide?
Sir, how to memorize this formula like this one?
Yeah, actually, this will come by practice, but since this is not there in the assignment, so you can, so since now, for the time being you're calculating, you're just solving the assignment, so you will have the formula with you, so you can just use it. In case of exam, I guess there will be a formula sheet which will be circulated to you before the exam, like you have to remember it and come for the exam, or these kind of datas will be given. Actually, I'm not sure how the exam pattern will be. So again, this is a very big formula, but if you see in majority of the cases, it will be written pointing due south. So if that is the case, then your surface azimuthal angle will be 0. So once that will be 0, your sine gamma, this entire term will be 0. So you just need to now memorize that sine phi and cos phi. So you can just find out, like, this is one tip that I have given, and you can also find out the other, kind of ways to make it simpler. Or there is one more way. Let me just 1 minute. Okay, I'll just let you know. I mean, for the time being, since you have the formula with you, then you can just use this formula and calculate it. But I'll just let you know as we go forward, like either by today or probably as we go, forward in this course, probably by tomorrow's lecture or something. Any more other kind of like technical doubts?
Sir, can you please zoom to your slide?
Actually, this is in the PowerPoint mode, right? So this will be the maximum visibility. Like,
Sir, slide.
okay, you want to that way? Fine then. Okay, so now then I can do that. Now is it visible? Okay. So let me just. I guess it will be like entirely covering. So I hope everybody is convenient with this mode, and now let's just proceed further. So I think there will be no more kind of technical doubts with this calculation. So now we have actually completed the very first part of the question, that is calculating the solar angles and angle of incidence. Now we need to calculate the tilt factors, that is for the radiation. That is, the tilt factors for the radiation is totally, there are three radiation. One is beam, that is the radiation that is coming directly and falling onto the surface. Then you have the diffusive radiation, which actually, due to the scattering by the atmosphere, the solar radiation, when it enters the atmosphere, some of the radiation will come and fall straight to the ground. Some kind of radiation, what happens is, it actually undergoes scattering in the atmosphere and they get diffused, that is, their direction actually gets changed during the course of coming from the sun to the ground. And then the other one is the reflective radiation, which gets reflected. As some of the light falls on the ground surface as well as in the atmosphere, some of the light will be reflected. So there are totally 3 tilt factors. One is due to beam, another is due to diffusive radiation, and another one is due to reflective radiation. This also we have calculated in week 1 as well as in week 2 as RB and RD. Here. So it's just that I guess there is, I mean, this value will be required actually for calculating the final value IT. So that is the reason I have just kept it at the end. But okay, it's fine. We can also start at this at first and then come back. So let me just zoom in the formulas. So your RR, that is the tilt factor due to the reflective radiation, for that the formula is rho into 1 minus cos beta by 2. What is the value of rho? Rho is 0.2. So this also we have previously discussed. Your RR value will be the value of rho. For calculating the value of RR will have two different values. One is 0.2 and another one is 0.6. So the value of 0.2 is for a ordinary ground surface, whereas in case of a snow covered ground surface the value of rho will be 0.6. So this is taken from the literature. So rho is 0.6 for snow covered, rho is 0.2 for your normal ground surface. So since we are installing this flat plate collector in Mumbai, so Mumbai we do not expect a snowfall at any part of the year. So the value of rho will be for an ordinary ground surface, that will be 0.2 into 1 minus cos beta. Beta is again, as I said, slope of your flat plate tilt collector from the horizontal surface. So that is 30 degrees divided by 2. So that value will be 1 minus cos, so 30 cos 30 into minus 1 this is cos 30, 0.866. So 1 minus 0.866 divided by 2 into 0.2, 0.0134, 0.013, up to 3 decimal places I have taken. So this is the tilt factor for the reflective radiations. Now you have to calculate for the beam radiation as well as for the diffusive radiation. For diffusive radiation the formula is 1 plus cos beta by 2. So that is cos beta is cos 30. So cos 30 value was 0.866 plus 1 divided by 2, 0.933, 0.933. RB is nothing but this RD is your tilt factor for the diffusive radiation. RB is the tilt factor for the beam radiation, which is defined as the ratio of cos of theta I divided by cos of theta Z. So your theta I is the angle of incidence, cos of angle of incidence divided by cos of zenith angle. So I guess if you calculate both the ways, then you will be getting the same answer. There was one query regarding how to remember the formula. So the value of cos theta can be minimized as this. This will be pretty simple, I believe now. Sin delta sin phi minus b plus cos delta cos omega cos of phi minus b, provided your gamma, that is your surface azimuthal angle, is 0. I guess in that case, if you calculate, this value was 0.784 and our angle of incidence was 0.782. Cos of our angle of incidence was 0.782. So this you can assume, you can take this as a kind of a short formula, but here again we have to make sure that before using this the value of gamma is 0 divided by your zenith angle. The zenith angle is nothing but here what the angle of incidence you take care you take it is, you have a flat plate collector which has an angle of making angle of theta degrees with the ground surface, and then the beam radiation and then the normal to the surface, that angle. Suppose let us take the flat plate collector is not tilted, let it be in the horizontal direction like this. So the normal will be in this direction, and let's say your sun rays is falling in this direction. That angle between the normal to the horizontal surface and the beam, the sun beam direction, is your zenith angle. So zenith angle is kind of assumption where we take the assumption as the value of beta equal to 0 degrees. So that is how we calculate zenith angle. So cos of theta z, and then for calculating this we have to go to the previous slide. What will be the zenith angle calculation? So the formula of zenith angle is this one: sin phi sin beta sin delta plus cos delta cos phi cos omega. Here I have not written omega, so the value here it would be cos omega will be there. Like for example, we have solved it in week 2 also, this question, the zenith angle question. Here. So the zenith angle is, yeah.
Cos theta z equal to sin phi sin delta plus cos delta cos phi then cos
Omega. That's what I'm just showing here. Over there it was missed somehow. So are you able to see this one? No, wait. So cos theta is cos theta z, that zenith angle is sin phi sin delta plus cos phi cos delta cos omega. The final term is cos omega. Let me just sin phi sin delta plus cos phi cos delta cos omega. So that is what is here also. So here the omega is missing, so that, but omega is minus 30. So since cos of minus 30 is same as cos of plus 30, so I have even like not written, but again there is no difference, both are same. So sin phi, that is sine of 19.07, delta is 13.54 plus cos of delta, that is your latitude 19.07, cos of your cos of delta, that is 13.54, cos of phi, that is 19.07, and cos of omega, that is cos of minus 30. But since both cos minus 30 and cos 30 has the same value, we have taken it here as cos 30 itself. So if you calculate, if you multiply this expression, then you will get 0.8722. You can actually, if you want now, you can actually use your calculator and check, because in this virtual calculator there is this thing, like you have to put the value and then you have to sign it up. So it's not like I can put sine of 19.07. so that is one of the issue. If you have a calculator with you, you can just solve this right now, so that you have a practice also. I'll just keep the formula. So if you calculate the value of theta z, it would be around 29.27 degrees. So when you calculate, please be mindful that the value of theta that you are going to take here is in terms of degrees, because there might be chances that you might cos inverse a radian and then the value will be completely different. So here the every value that we take towards calculation all are in degrees. Like even if you see our latitude angle, even during the week 1 I have told the latitude will not be available to you in terms of 19.07 or something. You will be having up, in case of like 28 degrees 26 minutes. So it will be something like this. This is just an example I am showing. 28 degrees will be there. And then it would be written as 64, sorry, not 64, let's say you can take 64 also, let's say 34. It will be given like this, or it will be given in terms of 28 double dash. So here your 28 represents the degree, let me keep 29, and 34 represents the minutes, and 29 represents your seconds. So this is usually the way the latitude of a location will be represented. So you have to convert this particular degrees or the in whichever is in minutes and degrees into minutes and seconds into degrees. So as I said, if this comes even in the class, week 1 lecture I have told, if you have a latitude which is given in terms of degrees, minutes and seconds, for degrees you divide, for degrees you just keep it as it is, for minutes you divide it by 60, for seconds you divide it by 3600, because it's like 1 hour has 60 minutes and 1 hour has 3000 seconds. So if you do that, then you will be getting, you can convert this into your the value of phi you can get in degrees if you just divide this by 60 and this by the 29 by 3600. So this is just as a model. For Mumbai you can actually Google and then check what is the value in terms of degrees and minutes, and then convert, divide the minutes by 60, add it to your 28 degrees, 19 degrees, then your value will be 19.07 degrees. So this is the value of theta z, that is 29.27. You can calculate. So we were there before, we just jumped in here. Your RB, that is the tilt factors due to your beam radiation, that is the radiation that directly falls on the surface without getting scattered by the atmosphere, is cos theta I by cos theta z. So cos theta I, you can use this formula, and this formula as well as the formula that we use for calculating angle of incidence is coming the same. So 0.784 divided by theta z, we just now calculated 29.27. So cos theta z will be 0.8722. So if you just divide this two, you will be getting 0.784 divided by 0.8722, 0.8988, 0.8991. So that's exactly the same. So here you now know the second part of the question, that is your value of RR, RD and RB, that is the tilt factors for the beam, diffusive and reflective radiation. So now we need to calculate the value of the instantaneous values of your beam radiation. Just let me show that. Instantaneous values of the beam and global radiation and the total solar radiation incident on your flat plate collector. So this is the next task for us. So here we do not know how much amount of the radiation is falling on the surface. Usually in a practical setting, if you are going to model a flat plate collector, you will be having the pyranometer and a pyrheliometer radiation values, because those are the two instruments. As we previously in week 2 also we solved a problem where we took the values of pyranometer and pyrheliometer's radiation, and then we calculated it. So your pyrheliometer calculates the beam normal flux, whereas your pyranometer records your global radiation. So these values are recorded values. So if you have a pyranometer and a pyrheliometer in your in the place where you are going to construct a flat plate collector, you will be getting these values. It will be a it's kind of a recording instrument, so you will be getting these values and then you can solve. So you know your IBN from pyrhelio, and from pyranometer you know your value of Ig. So if you know IBN and Ig, you can calculate the beam radiation IB and then your diffusive radiation. But since in this problem we have not given any data regarding that. For us, we have just given the date. The only data that we have with us is the date, that's all, and then the place and then the location. Here we just have only the the slope, the surface azimuthal angle, the date and the time. Now it's our responsibility to calculate the value of instantaneous beam, that is IB and Ig, and then your total IT, how much is incident onto your flat plate collector. So your IBN, this is the beam normal flux, that is the flux that is falling entirely directly on the in the normal direction, is nothing but is given by the formula A into e power minus b divided by cos of theta z. But here you don't know what is the value of A and B. So for August 16th specifically, in the literature you will find the values as A is 1107 watt per meter square, the value of B is 0.201 and C is 0.112. Let me just zoom this in more. And this is the formula. How to calculate your IB from IBN. So you don't know the beam normal flux also. So beam normal flux now we will calculate, because you know the value of A and B. So IBN is A times e power minus B by cos of theta z. So that's what is shown here. So your value of A, I have taken it as, over there it is given 1107 watt per meter square. Here it is 3985.2, because here I have calculated that watt per meter square in terms of kilojoule per meter square hour. So if you multiply this value into 1000 and divide that by 3600, you will get the value. So let me just calculate it once. I'll just show the calculation. You will get the value 3985.2. If you have calculators, you can actually calculate and check. You are just converting the watt per meter square as kilojoule per hour times meter square. That value will be 3985.2 into e power minus 0.201 divided by 0.8722. Here the value of B remains the same, that is 0.201, and cos theta z here you have calculated, so that value will be 0.8722. So if you calculate this value, you are going to get 3164.94. The specific reason why we are converting from watt per meter square to kilojoule per meter square hour is because the instantaneous flux should be represented in terms of the kilojoule per meter square per hour. That is the standard notation. So to get that standard notation, we are converting the value of A from watt per meter square to kilojoule per meter square hour. But if you want, you can also keep it in watt per meter square hour. There is nothing much difference. So any questions, or I guess I can go ahead. So now you know the value of beam normal flux, but that is the beam normal. So the beam that is falling normal to the surface, but that is not your value of IB. IB is the beam radiation that is falling onto your surface. So to calculate that, we have this formula, IBN times cos of theta z. So IBN, you know, 3164, cos of theta z is cos of 29.27. So if we calculate, the value of IB will be 2760.460. So let us just calculate this. 316 into cos of theta z, that is cos of 29.27, and that value will be 0.8722. 2760.460 kilojoule per meter square hour. So now we know beam normal, and from there if you see the formulas, so you know beam normal, we need to get the global radiation, but we know that global radiation is the total amount of solar radiation coming from the sun, which is nothing but is the sum of the beam radiation, that is the radiation that is falling onto the surface without getting scattered straight, plus the diffusive radiation that gets scattered because of the atmosphere. So this is the sum. So we know IB. If we calculate ID, we can get the value of IG. But to calculate ID, you need this formula. ID is nothing but C times IBN. You know the value of C, 0.122. IBN is known, 3164.94. So you can now calculate the value of ID and let me know. In case if you are having any confusion regarding how to get the value of A, B and C, all these will be given to you as given data, because these values are actually taken from literature. So these formulas you don't need to actually memorize, this is just for the practice purpose, because usually in a question the value of IB and IG will be given. As such, as I said, in a practical setting you cannot calculate the value of IG and IB using this literature, because then the model that you are going to develop may not be exactly accurate. So there you will be having the readings of the pyrheliometer and pyranometer, but this is just for practice purpose on how to actually calculate the value of, like, how does a pyranometer or pyrheliometer calculates the value of global and beam radiation. So we should know that. So for that conceptual purpose we are actually calculating here. This, in majority of the exams you may not be getting like calculation of this IgIB, but this is for, you know, the kind of your own benefit, we are solving this here. So ID is nothing but C times of IBN. So you can calculate, C is 0.122, IBN is 3164.94, and then let me know what is the value of ID. It's just multiplication. Anybody? Because this is just multiplication. So okay, so we will just, yes, 386. Let me just, okay, let us just calculate, because you have responded, so we will just calculate. So 3164.94 into your C value, that is 0.122, 386.12. Is it what you got? Yeah, so this will be the value. So you have your, now you know your value of Ig, you know your value of Ig, you know your value of Ib. So now you can actually calculate your sorry, you know your value of Ib, Id, you can calculate your value of Ig now. So you can actually calculate and let me know. So here Id you have already told us 386.122 kilojoule per meter square hour. Here you know your value of Ib, that is 2760. So what is the sum of both? It's just addition. So let me also do here. 2760.460 plus 386.122, that is 3146.582. So this is the value here. Ig, that is your sum of beam plus diffusive. So this is the sum. So in a real practical case setting, I am repeating again, the value of Ig will be calculated by your Pyranno, and your IBN, not the value of Ib, the beam normal flux will be calculated by Pyhelio. So with that you can actually, in that case this problem will be simplified to a lot more extent. It will become a lot more easier, but we need to have an understanding on how does this pyrheliometer or pyranometer actually calculates this global radiation. So it's just for the practice purpose that we are actually calculating, manually the values of IBN, ID and Ig also. So your value of Ig is 3146.58 kilojoule per meter square hour. Now you know your value of Ib, Id, Ig, and you know RR, RD and RB, that is your tilt factors for reflective, beam and diffusive radiation. So now you can calculate the total instantaneous global radiation, total instantaneous solar radiation falling on the flat plate surface. So I'll just show the formula, you can actually calculate it. This is the formula. Let me just zoom in more.
Unit of Ig, Ib, Id, all the unit of kilojoule per meter square hour.
Yeah. Everything is in kilojoule per meter square hour.
So what is like that kilojoule per hour? What is equivalent to kilojoule per hour?
1 watt is actually equal to 1 joule per second. So you can change it that way also. I mean, it doesn't, kilojoule per meter square hour is the standard SI way of using it. If you want, you can also write it in terms of watts. 1 watt is 1 joule per second. So that is that unit conversion alone. So here you know the formula for IT, that is your total instantaneous solar radiation falling onto the surface of your flat plate collector. So that is IBRB plus IDRD plus RR of IB plus ID, because the reason why RR is multiplied with both IB and ID, as I said in the previous discussions also, is because both of these radiation, when they fall on that ground surface, they can a very small quantity of this radiation can get reflected. So that is the reason that reflective coefficient, the tilt factors for the reflected radiation, is multiplied with both IB and ID. Now calculate the value of IT and let me know. It's simple, you just need to multiply and add the numbers. Let me just do parallelly. So your IB value is 2760.460 into your RB value is 0.8991 plus your ID is 386.122 into your RD is 0.933 plus your IB plus ID is your global radiation, so IG value is 3146.58 times your RR 0.013. So the total IT that is falling onto the surface, flat plate collector surface, is 2883.0869. Oh, sorry. To 883.24 kilojoule per meter square hour. So this is the, let me be more repeat again, this is the instantaneous, the total instantaneous value of the solar radiation falling on the flat plate surface. Let me put it in a wider screen. This is the instantaneous value. There is another value, so this is not the average value that we are getting. This is the instantaneous value at a particular instant of time, that is exactly at 14 hours on August 16th at 14 hours on August 16 with the beta value of 30 degrees, flat plate character pointing towards the south surface with the assumed values of A, B and C to calculate the IB, IG and ID. The instantaneous value of the radiation that can fall on the flat plate collector is 2883.24 kilojoule per meter square hour. Again, we have already discussed in week 1 the monthly average and the daily hourly average and monthly average. That is, you take the instantaneous value at every hour and then divide and then take the average of it, and then for the monthly you take it for every particular day and then take the average of it. So those are different. This is the instantaneous value alone. So here our primary focus is on calculating the instantaneous value. So your value of IT is 2883.24 kilojoule per meter square hour. So the first part of the question is done. You now know solar angles IB, IG, beam radiation, instantaneous beam radiation, instantaneous global radiation, instantaneous diffusive radiation and the total instantaneous solar radiation falling on the flat plate collector. Now your sunlight has actually fallen onto the flat plate collector. Now this sunlight that actually falls onto the flat plate collector has to be absorbed. So for that we need to start calculating or understanding the process of how a flat plate collector works. So as I said previously in the last last week 2 live interaction session as well, so when the light falls, first it falls onto the transparent glass cover and then it undergoes refraction. After getting refracted from the glass plate, what it happens is it actually goes to the absorber plate. So between this glass plate and the absorber plate, it's only the air is only filled, it is filled with air, and then this absorber plate is actually coated with the black, it's kind of a selective surface to increase the absorption capacity, that is to increase the amount of the solar radiation that can be absorbed by the plate. This absorbed solar radiation, then that particular heat whatever the absorber plate has gained goes to the fluid tubes. So the fluid tube is a kind of a provision for the fluid to flow. So here the heat is actually taken up by the fluid. The heat that is taken up by the fluid actually goes to the storage tank or for different kinds of application like space heating application or some kind of electricity generation or storing that particular energy for a different period of the day or a month or particular period, particular month of a year or particular season and other stuff. So here first refraction happens, then the light that gets refracted falls onto the absorber plate and then to the fluid tubes the heat gets transferred. whatever the heat that is gained by the fluid that is present in the fluid tube is called as the useful heat gained by the fluid. So the reason why here you actually mention the word useful heat gain is because when this happens there will be certainly losses. So first the light is getting refracted into the from the glass surface into the air medium. So when that happens, the light gets refracted and it enters into the air medium. So when that happens there will be convective radiation losses, and also when it gets absorbed by the absorber plate, there will be a particular we do not have an absorber plate which has a thermal conductivity of infinity. In our ideal case we can assume that the thermal conductivity of a flat plate collector can be infinity, but in a practical aspect we do not have that kind of uh, a provision for having or a material which has a thermal conductivity which has an infinite thermal conductivity. So there will be losses from that, and then the heat has to be transferred from the absorber plate to the fluid tubes. So again there will be a heat transfer coefficient, the value of H, and again there will be, during this process there will be convective losses. Apart from that, even though we keep that entire flat plate collector in a thermal insulation casing, if you let me just show the figure, this is the So this is the thermal insulation that is actually available, but still every thermal insulation from there also, it's the insulation is made in such a way that majority of the energy that comes from the absorber plate or from the solar radiation that falls on the surface is not lost. But again, every thermal insulation we cannot assume it will completely block the heat. So again there will be some amount of the radiation that will be diffusing out to the environment. This is the working principle or the way how does the heat gets absorbed by the fluid tube. So now we know the principle or we know how the system works, so we can go towards calculating for our system which we have taken today, how much will be our efficiency or how the light will refract, undergoes refraction, and how much amount of the useful heat will be gained, what will be the temperature of the fluid that will be coming out of our tube, what will be the efficiency of our flat plate collector that we are designing, everything we will see today. So for this let me keep it in PowerPoint mode because I have to say this question. So here we consider a absorber cover system for a flat plate collector. Our material is glass. So here we have considered the number of covers, that is the glass plate covers as 2. If you see in the video or in case of majority of your assignment problem, the number of covers which you will be having is 1. So what does that mean is, I could have shown that. So this will be a flat plate collector, this will be a glass cover, and then in case of a one glass cover system, after this glass cover you will be having your absorber plate, but in case of a 2 cover system there will be one more glass cover, and after that particular glass cover you will be having your absorber plate. So which means there will be 2 glass covers. So do we have a Jamboard facility? Let me just show it the picture. So I hope you are able to see my Jamboard. So this is one, and then in case of the other design, here you have absorber plate, and then here you have your absorber tubes. So this is one cover system, but whereas in our case we have totally 2 covers. let me just redraw this. So these are the fluid tubes. So this is a one cover system, whereas in case of our two cover system which we have assumed here, this is one, this is one, this is the second one, and then you have one more. So here you have two cover systems. And then the thickness of the cover is given, the reflective index of the glass, because it actually refracts through a glass, so there will be a refraction phenomenon, and then the refractive index is given, extinction coefficient, we have all the different values. Now what we have to calculate, so the light is getting refracted, so angle of refraction, some amount of the light will get transmitted, so it actually travels through the air, so transmittivity based on reflection, refraction based on absorption, the transmittive absorption product, and the solar flux. The way I have given the subheadings is similar to what is there in the assignment problem. So here the light is getting refracted. So we need to actually calculate what will be the refraction angle. So you know the Snell's law, as we discussed last week also. The Ni is your Ni sin theta I equals Nr sin theta R. So Ni is your refractive index of the incident medium. Theta I is your angle of incidence. So this is theta I, and your theta I is nothing but here is your angle of incidence, because your flat plate collector is the solar radiation actually falls on your flat plate collector. So and that light is only going to get refracted into the glass cover. So that theta I will nothing but is your angle of incidence. Oh, sorry. So theta I is 38.56. Nr is your refractive index of the refracted medium, that is where you are going to, where your light is going to refracted, and theta R is your refraction angle, that is this. So this is Snell's law. This is a very elementary equation, like 10th class equation. Ni sin theta I equals Nr sin theta R. So I guess you will be able, everybody will be able to calculate the value of theta. So I expect from the audience to let me know what will be the value of theta R. It's simple. It's just you have 1 into sine of 38.56 is equal to 1.8 times sine of theta R, and then if you just take that 1.8 to this side and then do the sine inverse, you will get the value of theta R. So what is the refractive index of the angle? Sorry, what is the refraction angle? Yes. I'll just write what will be the refraction angle. So let's calculate the angle of refraction. So let me just use the calculator. So sine of 38.5. This is the angle of incidence that is falling onto your flat plate collector. So sine of 38.56 is 0.623 into 1. So that is your refractive index of the incident medium. So air. So for air, the value of refractive index is 1. Divided by 1.8. So this is sine of theta r. So your sine of theta r is 0.346. So you have to take your sine inverse. Sine inverse is 20.26. That's what is written, 20.26. And I have shown also 1 times sine of 38.56 is equal to 1.8 times sine of theta r. So your sine of theta r will be 0.623 divided by 1.8, that is 0.3463. So the if you take the theta r, the sine inverse value, you will have theta r as 20.26 degrees. So angle of refraction in the glass medium is 20.26 degrees. So you now know the angle of refraction. Now after this you have to calculate the values of, if you go to the previous slide, we will get to know. You have to calculate transmissivity based on reflection and refraction. So yes, when a light gets reflected and refracted, there will be a transmissivity component. Okay, yeah, sure. Yeah. You can view my slideshow. So now angle of refraction you understood, right? Like that is simple elementary equation. Ni sin theta r equals to Na sin theta r. Oh, you are not able to see the full question? No, because this is there in the slideshow and here I can see the full question. Wait, let me just minimize let me just zoom out now. Okay. So this is your angle of refraction, and this is the question. So now we have calculated the angle of refraction, that is 20.26 degrees. Now we have to calculate transmissivity due to the reflective, refraction and your absorption component. So let us see how to calculate that. Now I will zoom in because I have to show. So here, your rho 1 and rho 2 are nothing but they are the okay, or I'll just show this slide. That is a very congested slide. So your rho 1 and rho 2, your rho 1 and rho 2. Your rho 1 and rho 2 are nothing but the reflection and the refractive components. So so that how do you calculate is sine square theta r, sine square of theta r minus theta I divided by sine square of theta r plus theta I. So these are the two components of the the polarization components of the reflection and refraction. So theta r is 20.26, theta I is 38.56. Similarly for theta r plus theta I. So 20.26 minus 38.56 will be minus 18.3 and then the addition will be 58.82. So now you have to take the sine square. So sine square of minus 18.3. So as I said, for a sine of a negative angle, it will be negative of that sine angle. But since here there is a square, so negative times negative will be a positive. So 0.098 divided by sine square 58.82, that is 0.7319. I'll just show the minus 18 point, I cannot show. minus 18.3 and sine of that to the power 2, 0.098 and sine square of 58.82. So 58.82 and then take the sine value and then square it. 0.7319. So if you take the ratio of the two, then your value will be 0.098 divided by 0.7319, 0.13389, 0.1339. So that's just a bit of an approximation. Now another polarization component due to reflection and refraction is rho 2. Rho 2 is nothing but tan square theta r minus theta I divided by tan square of theta r plus theta I. So this will be remaining the same. It's just that over for rho 1 this thing is sine and for rho 2 it is tan. So let's calculate that as well. Minus 18.3 and tan of that will be minus 0.33 times square 0.1093 divided by tan square of 58.82. 2.7307, 2.730. So if you take the ratio of both 0.04, 0.040. So now you have the value for both the components. Now you can calculate the transmissivity due to reflection and refraction. So tau r1 is nothing but 1 minus rho 1 by 1 plus rho 1. Tau r2 is nothing but 1 minus rho 2 by 1 plus rho 2. Tau r, that is your final, both due to reflection and refraction, that sum of transmissivity due to reflection and refraction is tau r1 plus tau r2 by 2. So you know rho 1 and rho 2. Rho 1 is 0.1339 and rho 2 is 0.04. So let me just write it here. Awesome. I'll just write P1 is equal to 0.1339 and rho 2 is equal to your 0.040. So you can just, this is again it's about substitution. I guess I can get to know the value of the tau r1 and tau r2. This is the formula. So I can get to, I think this is just calculation, so you can let me know. So I'll just calculate it here. 1 minus rho 1, rho 1 is 0.1339 divided by 1 plus 0.1339, 0.7638, that is rho 1 tau r1 value. Is it the same that others are also getting? 0.768, I guess. 0.763. But over there, whatever, this formula is actually has a particular limitation. So this formula, that is this tau r1 is equal to 1 minus rho 1 by 1 plus rho 1 is specifically valid only when you have a one glass cover system. So the formula actually changes if it is a multiple glass cover system. So the general formula is Now, what is the general formula? This is given even in the video lectures if you see, but I am writing it here once again. So, tau, that I am here just representing t so that we can make sure that it is quick, because otherwise it will take some time. 1 minus rho 1 divided by 1 plus 2m minus 1 times rho 1. Let me just expand this. So, here m is nothing but, here it depends on m is the value of the number of glass covers. So, ours is a 2 glass cover system. So, the value of m is 2. So, here the formula would be, this is under an assumption that green color box what you see is under an assumption that if you have a 1 glass cover system, but we have a 2 glass cover system, as you see in the question. Let me zoom out and show the question once again. Here we have written the number of covers is 2. Our number of covers is 2 here. So, the light that is actually going to fall will go under 2 times refraction. So, m is the number of glass covers. So, let me just zoom in again. The light has to go through 2 different glass plates. So, in that case your m value will be, for us m is 2 here. So, 1 plus 2 times of 2, that is 4, 4 minus 1 is 3. So, that is the reason tau r1 we have written as, zoom it, 1 minus rho 1 divided by 1 plus 3 times rho 1. So, rho 1 is 0.1339. So, 1 minus 0.1339 divided by 1 plus 3 times 0.1339. So, the value will be this 0.679. Let us just calculate quickly. Divided by 1 plus 3 times 0.1339. No, wait. 1 plus 3 times 0.1339 1.407. 1 minus 0.1339 is 0.8661. 0.8661 divided by 1.4, I hope it was 1.4. Excuse me, 1.4017, sorry, 0.8661 divided by 1.4017, 0.61789. I have taken it here, it has 0.6179. Now, I will leave it to you to tell me what is the value of tau r2. Tau r2 is nothing, here you have to replace the value, same formula, 1 minus rho 1 by 1 plus 3 rho 1, but you have to replace the value of rho 1 divided to rho 2, which is 0.04. So, what will be that value of tau r2? I will just write here. What will be the value of tau r2? So, these values I will be doing the modification when we will be uploading the PPT to the NPTEL portal. So, this PPT will be available to all of you for every week. So, if you see in the NPTEL portal, in the section where you can see week 1, week 2, week 3 lectures, over there at the bottom you can see a problem solving session. So, if you go to that, you will have a link. From that link you will be directed to a Google Doc, a Google Excel sheet, and there you can calculate the value of you will actually go to a Google Excel sheet, From there you can actually access both the lectures recording. This lecture will be is getting recorded and will be uploaded to a YouTube channel. If you click the link, you will be directed to the YouTube channel, and this PPT will also be available. Week 1 and week 2 PPTs are actually uploaded already, so you can go and view them. Week 3 we will be uploading it very soon, probably by today or after finishing tomorrow's lecture. Tomorrow we have the week 4 lecture. After that I will be updating both the PPTs together in that portal, so you can view there, and I will make the necessary modification. Like here I have written P1, so I will just make it as row 1, and then it will be available to you before Wednesday of the coming week. So now let me know the value of tau R2. Yes, it's just simple. 1 minus 0.04 divided by 1 plus 3 times of 0.04. Anyway, I'll calculate that here. 1 minus 0.04 will be 0.96. 1 plus 3 times 0.04 will be approximately 1.12. So 0.96 divided by 1.12. 0.857. So tau R2 value, I hope others have calculated, is the value is 0.857. So you have your tau R1, tau R2. So now the total transmissivity due to the reflection and refraction, both that component together, it will be tau R is equal to tau R1 plus tau R2, sorry, divided by 2. So that value will be 0.857 plus 0.6179. So the average of these two, what is the value? We will just calculate here. 0.6179 plus 0.857 divided by 2, 0.73745. Let's just take tau R is equal to 0.7374. Let us just keep it up to 3 or 4. 3 decimals is more than enough, not necessary beyond that. So this is your transmissivity due to reflection and refraction. Now we have another one component, that is absorption. So let us move towards that. I hope here you do not have any confusion. Like, even though these are like, there are many formulas, but the substitution wise, it's just that we are substituting the values and then identifying what will be the reflection and the refraction component of the value of the transmissivity. Now you have your, again, after reflection and refraction there will be transmissivity because of your absorption also. So we have to account for that transmissivity as well. So that formula is this one: tau alpha is equal to e power minus k delta c by cos theta r. Here theta r is your refraction angle, because since it's actually going through the glass plate cover and then after that it is moving through the air medium, so the value of, we will consider here the value of theta r. K is your extinction coefficient, that is the extinction coefficient of the glass plate that you are taking under consideration. Let me just move to show extinction coefficient of the glass. Here we have taken it as 10. And then your delta c, if you see that is nothing but it is your spacing between the two glass plates that you are taking. So this is the values. So your tau alpha is e power minus 10 into 3 into 10 power minus 3 divided by cos of 20.26. But if you see here, there is an extra 2. This 2 actually comes because you are having 2 glass covers. So if there are 3 glass cover, this value will be 3. If you have 4 glass covers, this value will become 4. So as I said, as you keep increasing the number of glass covers, you have to keep multiplying that. You have to keep taking that under the consideration, because your light is going to get refracted every single time as it goes from one medium to that of the other. So you have to keep on what do you say, some amount of the light is going to get reflected because it's a glass cover, and then some is going to get refracted, and then again reflected, refracted, reflected, refracted. So the number of the glass plates, glass cover plates will affect. So this value will be depending upon the number of glass covers that you have in the system. So here, since we have 2, we are multiplying it with 2. So tau alpha will be, if you calculate this, your value will be 0.938. That is 2 into 3 into 10 power minus 3 2 into 3 is 6, 6 into 10 power minus 3 into 10, this divided by so 0.06, so 20.26, for that the cos value will be 0.938. so 0.06 divided by 0.938, this is your value. So this you have to take the negative, it's 1.06. so let's just go to the exponential. Here I guess we do not have exponential. Okay, so the value of E will be the value of tau alpha will be 0.938. so you can use your calculator. Let me just show here. So E power minus 1.06. Yeah, that is the same, 0.938. Now after this, so you now know the transmissivity due to the reflection, refraction, as well as that of the absorption. The question that we have next is, what will be the product of those? So transmissivity, absorptivity, so this is transmissivity, absorptivity product based on the beam and the diffusive radiation. So that this is, as I said, tau is tau r times tau alpha. So that will give you a total transmissivity, that is due to all the components, not just reflection, refraction, but also due to absorption. This tau alpha we have calculated now 0.938, tau r we have calculated previously 0.73745. so if you multiply that, you will get 0.691. 0.7374 into 0.938, 0.691. so that is your transmissivity due to reflection, refraction, and the absorption component, all the three together. So because every time when a light falls on a glass cover, it undergoes all these three phenomena, so we have to take under consideration everything. And this tau alpha is equal to e power minus k delta c divided by cos theta r. This formula which is given here is called as the Boyer's law, which gives the transmissivity due to the absorption of the radiation. And the value of the k, for the information purpose, it will be between 2 to 40, that is your extension coefficient of the glass. Here we have taken 10. Now we know that tau, that is your transmissivity. We need to know the tau alpha of the beam of the radiation particular to beam radiation and then the diffusive radiation. So that is actually calculated by this formula. This is specifically for beam, and here you will be having two terms. Your alpha p is nothing but your absorptivity of the plate. So now the light has got refracted and then it goes through the air, it has went through the air, and then now it's going to fall on the alpha p, on the absorber plate. So the absorber plate will have a particular absorptivity, like it is not a black body, or it's not a black body, so the value will not be 1, so it will have a particular value, because black body is a ideal case. In a real case you will not have anything for which the alpha will be 1. So alpha p is your absorptivity of the plate, and rho d is nothing but the your reflective diffusivity, that is diffusive reflectivity, that is rho d. The formula for calculating the value of rho d, we saw it last week. Rho d is tau alpha times 1 minus tau r. So we know rho d, or you can also take rho d value as it's better to calculate. Actually it will come near to about 0.2. The diffusive reflectivity, that value will be 0.2, but you can calculate using that formula, tau alpha into 1 minus tau r. So here absorptivity of the plate, let us go to our question to check what is the absorptivity of the plate. Plate absorptivity and emissivity is here 0.95. That is 0.95. So your tau alpha b will be tau times this formula divided by 1 minus of 1 minus alpha p into rho d. So tau is 0.691, 0.95, and rho d is tau alpha into 1 minus tau r. We can calculate that value. So 0.938 into 1 minus tau r is 0.7374. No, this is wrong, sorry. Your 1 minus 0.7374 is 0.2626. So 0.2626 into your tau alpha, that is tau alpha is 0.938, 0.24. So that's what we have taken. This value you can actually assume it as taking it as 0.2, because the diffusive reflectivity, that value is kind of like taken as a constant 0.2, like it's kind of assumed, because it's actually pre-calculated value for the diffusive radiation. So you can take it as 0.2. So if you calculate, your tau alpha b will be 0.663. So this is only for your tau alpha of b, that is transmissivity absorptivity product due to beam radiation. Now similarly we have to calculate for reflective radiation, but in case of reflective radiation, what happens is, here for beam radiation the light falls on the horizontal surface, so you know the angle of incidence, because the beam is going to travel directly and fall onto the surface. But in case of your diffusive radiation, that will not be the case. The diffusive radiation will be like scattering in all the directions. So over there, finding the value of theta I will be difficult, because it will be scattered in any directions. You may not have an idea. It all depends upon how the scattering happens in the atmosphere. So in that case, we have to take that, we consider it, like we assume, or we take it as an assumption, we keep it as theta I is 60, like since it is going in all the radiation, so we have to take a particular kind of average, or like this will be like as a standard reference, because otherwise we won't be able to calculate the theta I. Then it will be like the calculation will be tedious, because you have the multiple directions the light will be getting diffused, so it's not possible to calculate for each value of theta I, then that will be too much. So here we take it as an assumption that for all the that we account for all the diffusive radiation by considering the value of theta I as 60 degrees. So the thing is, you have to actually proceed, this entire calculation has to be repeated again. By assuming the value of theta I as 60, you have to repeat the entire calculation. Let me show in this slide. uh, Let me just put it in a, let me just minimize it. So you have to here take the value of, use the Snell's law, take the value of theta I for the diffusive radiation as 60, calculate the value of theta R, then put the theta R in this rho 1 and rho 2, the polarization components due to reflection and refraction, and then use that to calculate tau R1 and tau R2, then the final tau R, and then tau alpha. And then after getting tau alpha and tau r, you can get the value of transmissivity due to all the contribution from absorption, reflection, refraction. Then you have to calculate the value of tau alpha d. So the entire process that we have discussed for the past 1 hour has to be repeated again. So in order to minimize that particular effort, I have already pre-calculated. So I have written repeat the calculation for the value of theta I, that is 60. If you do that, you will get these values of theta R, rho 1, rho 2, tau R1, tau R2, tau R, tau alpha, tau, and tau alpha d. So this has to be like repeated. So I guess we can do this, and then we can, yeah, we will do this, because since it's just given, you can try and let me know whether the values are matching, like the value of theta R and all. So let me also parallelly do it using my virtual calculator. So here our theta I is 60, so 60 sine 60 is root 3 by 2, 0.866 into 1 divided by 1.8. Yes, oh no, 60 sine of 60 into 1, 0.866, let us remember 0.866 divided by 1.8, 0.4811. Now sine inverse of this angle, 28.75 degrees. This is your value of theta R. Now you have to calculate rho 1. So rho 1 is, how do we calculate rho 1? Rho 1 is sine square theta r minus theta I divided by theta r plus theta I. So that value will be theta r is your 28.75, right? So 28.75 minus 60, that will be minus 31.25, and 28.75 plus 60, that is 88.75. So minus 31.25, that sine value, square it up, minus so minus 31.25 and sine of that minus 0.518, minus 0.518. So minus 0.518 0.268324 divided by 0.268. Okay, then sine square of 88.75. So 88.75, and then we do that sine. Yeah, this and then square of. So our initial value was 0.268 divided by 0.999. So again, since the value of sine square of 88.75, that is close to 90, so sine of 90 will be approximately 1. So your value of rho this will be approximately 0.2628. So again, if you just keep calculate, if you calculate, you will be getting all this value of rho 1, rho 2, tau r1, tau r2, tau alpha d, and tau. So this you can take it as a kind of like home task, because now you know the value of theta r. So theta r is 28.75. So once you know the theta r, that is the base, then you can calculate rho 1, rho 2, tau r1, tau r2, tau r, tau alpha, tau, and then tau d. So this I will leave it, because again it will take a lot of time if we start solving each of them. Let us come to the conceptual part. So here your S, so the reason why we calculated all this is to find out how much amount of the solar radiation that is falling on the surface is going to be absorbed or utilized by our flat plate collector. As I previously said, it is not necessary, or the amount, in a practical case, the amount of light that is going to fall on your flat plate collector and the amount of light that is going to get absorbed by your flat plate collector will not be the same, because there will be kind of loss of radiation, loss due to convection, re-radiation losses, many kind of losses will be there. So these two values will not be the same. So we need to actually know, if suppose this much amount of the radiation is going to fall on my surface, how much amount of the radiation will be harnessed by the flat plate collector, how much amount of the radiation will be used by my flat plate collector, or how much amount of the energy can my flat plate collector use, so use it for my final application, like how much amount of the heat am I going to get for the final application. So S is nothing but the solar flux, that is the amount of energy, amount of solar radiation falling on the flat plate collector per unit surface. Like solar radiation, the intensity per unit surface of the solar collector is your S value, that is the solar flux. That is calculated by this expression, IBRB tau alpha b plus IDRD plus IB plus ID times RR. As I said, both the beam and the diffusive are going to get reflected, and this is multiplied tau alpha d. So if you multiply them, you will be getting the value as 1953.4863. So let me just, since we know, okay, we didn't calculate IBRB separately, so let us just calculate that. Tau alpha b, now you know it's 0.663, because we calculated here 0.663. So let's calculate the value of S, that is how much amount of the energy, that is flux, that is your flat plate absorber, flat plate collector is going to absorb. 2760.406 into 0.8991, that is your RB value, times 0.663. 1645.487, this particular term 164.513 plus now this one calculation IDRD. ID 386.12 times 0.933 plus reflective radius 360.24. Let us keep in that in mind. RR is 0.13 times your 3146.56, this one plus 360.24 times your tau alpha d. Tau alpha d value we calculated it to be around 0.767, 361.007, 300, and that's what is, I guess there might be some calculation error because since I was doing it from my memory based, I didn't check here. If you calculate, you will be getting somewhere very close to this. So the value of your final S will be 1953.4863. So if you see here, you can actually check the total instantaneous solar radiation that is falling onto your flat plate collector is 2883, but what is going to get absorbed is only 1953. So you can see the amount of the radiation kind of how much is going to absorb. You can get a relative idea. So how much is actually getting diffused out or wasted or is not something that is going to get collected by your flat plate collector. So this is the so with this we actually end our the second part of our question. Now comes our third part. Yes. Oh yeah, actually that's yeah, let me just show. So tau alpha d, we actually, the thing is, you understood that we used theta I, that angle of incidence, and then we calculated rho 1, rho 2, tau r1, tau r2, tau r, tau alpha, tau and tau alpha d, right? Tau alpha b. Similarly, we have to also account for our diffusive radiation. So some amount of the light is going to get diffused, so we need to actually account for that also. So since the diffusive radiation, the solar radiation can get diffused in any direction, we will not be having, we cannot like count for every single direction. So as a kind of a standard reference, like which account for all of the diffusive radiation, we take the value of theta I as 60. But the solar radiation is also going to fall onto the surface of your glass cover. So these radiation will also undergo refraction. Here we have taken the theta I as 60 because we are going to account for all the diffusive radiation. So you have to get all these values, theta r, rho 1, rho 2, tau r1 for the diffusive component, because they are also going to get refracted. So you have to repeat the entire procedure what we did for beam radiation for diffusive radiation also. But since it's the same procedure that we are going to follow again, I have already calculated and the value of tau alpha d came around 0.767. So that's what we are actually multiplying here. Did you get like, yeah, it's just that I mean it will be like a very mathematical, it's just a very mathematical stuff, so you can keep, it's just that you have to repeat the calculation. So instead of that, I just assumed, I just calculated it previously and I am showing it here. So this is your value of S. So now the second part of our question is done, which is identifying how much amount of the solar flux will be absorbed by our flat plate collector. Now this is only one part of the question. So we know how much amount of the solar flux is going to get absorbed, but how much amount of the flux that is absorbed is actually going to get used up for our application, or how much is actually the fluid that is flowing through the tube is actually going to take. We do not have an idea on that. So for that we have to again we have an entire question that is left out, but since now we do not actually have time, the class was supposed to be from 5 to 7, like it was actually planned that we will be able to finish off this portion, but it's fine. So this particular this thing is we have to solve. So this we will be taking up in the next class, that is tomorrow from 5 to 7 p.m. we have a class schedule that will be for a week 4 session. This class was supposed to be conducted previously, but on that day, due to abrupt internet disruption throughout the institute, we were unable to conduct, and then after which we were unable to actually find a slot for conducting this class, and today we are conducting. So my apologies for that, apologies for that. So so this particular C part of that question we will take it tomorrow, because let us actually settle our mind, because there is a lot of things that has been covered today, calculating the transmissivity, angle of refraction, absorption coefficient, and many more stuff. So let us just stop here today, but that is only for this question. With we have some more time left, like 2 or 3 minutes. Let us just go to week 1 assignment discussion. Since your uh, solutions has already been shared with you in the NPTEL portal, I guess now I can discuss those questions with you. Let's go quickly through these questions. So the first question is, part of the total radiation of the sun that reaches the earth's surface after a change of its direction due to scattering by the atmosphere is called. So since the answer is already present, so I'll just tell the answer here, or if you guys want, you can also like unmute your mic and let me know the answer. This is very easy actually. I mean, uh, out of that, two options are wrong, B and C. It cannot be infrared or it cannot be ultraviolet. So it's just the beam or the diffusion. And as we discussed now, that if a particular radiation that is coming from the sun is going to get scattered by the atmosphere, whatever the radiation that directly falls on the surface is called as your beam radiation. So now there is a change in the direction, it's written, due to scattering by the atmosphere. So it will be your diffusive radiation. This is the answer. Then the next question is the ratio of the beam radiation flux falling on the tilted surface to that falling on a horizontal surface. Again, this is your like, as I said, how much amount of the radiation will fall onto your horizontal surface and your tilted surface. So that is nothing but it's your slope. So the value of IBN and IB, if you remember, so that is nothing but your tilt factor. So like that we have other questions, but let me just check. I guess the answers has been previous has been released out, right? The answer keys. Let me just check once. Does anybody know? I guess the answer keys has been released already. Just a second. Just a few 1 or 2 minutes, I'll be able to know. So I guess the answers has been answer key has already been discussed. I mean, sorry, has been released. Oh, okay, okay. Probably, I mean, I'm also kind of like that is, my questions are also here. It's not just only the week one assignment question. I guess from here, this will be the week one assignment, right? Because this calculate the hour angle if it is 9:30 a.m. IST is oh no, actually, I have taken only those questions which are kind of like people might have doubt, because if you see that question, I guess that's a very you can easily say it's the answer is biomass. I guess that is the question if I am not wrong. Yeah, everything will be there in the PPT. Like we will be uploading it probably mm, tomorrow or probably maximum by Wednesday. Over there, you will be knowing what will be the. I mean, these questions will be which one? Yeah, I mean, if you see here, there are few questions which are actually taken from your assignment for this for the week one, and there are also few of my own questions. So this will be there. This will be there. All these 7 questions. This will be there. But since I guess it has been released. Okay. Anyway, I'll confirm this once, and then we will discuss this tomorrow, because tomorrow we will be finishing off that particular part of the equation, and we will be having time, so we can discuss this part of the those 5 or 6 7 questions tomorrow. So I hope does anybody have any doubt in what we have discussed today? Okay, so I guess others anybody has any doubt? Okay, so I guess if in case if nobody has a doubt, let me just stop presenting. Yeah, so I'll just conclude the session. So yeah, thank you very much for joining today's week 3 live interaction session, and I sincerely apologize for what happened last week. We were unable to conduct the live session due to internet disruption. So I take this as an opportunity to thank the course instructor, Professor Vaibhav Vishant Gaut sir, and Professor Anand Lakshmi ma'am, as well as the NPTEL team for providing me this opportunity to interact with you all, in a week live interaction session through this particular platform. And let us actually meet for the week 4 live session in a regular schedule, Sunday, tomorrow 18th February from 5 to 7 p.m. the same time. And yeah, thank you very much for joining, for taking your time and joining for today's session, and we will meet tomorrow. Bye.